thing. Oh, goody. Okay. Yay.
I thought vectors were like the points of the triangle.
This is the
What is
Those
that?
are vertices.
It starts with a V, doesn't it?
So B and a L, but that's all.
I don't like a triangle is good enough.
There's R's in both of them.
Yeah.
The fact that I have to think about it is that
Yeah, no problem. Perhaps.
I was like, no, okay, no.
So a vector is just a line segment that has a direction and as a magnitude or a length. Typically, our vectors start at the origin 0, 0, and then go to a coordinate point on our rectangular coordinate system. Sometimes vector can also, though, be just a line segment connecting 2 points where one of them is not the origin of our coordinate system. So if we are looking at vectors, there are 2 ways to identify a vector or name them. The first way that we can name them is naming it by its initial point and its terminal point. So here we would have the vector PQ, assuming that neither P nor Q lie on the origin or the point 0, 0. Another way that we can name a vector is we can assign a singular variable to represent that vector. So for instance, this could be vector A, and we would just say vector A. You could also have these around them. They look like parentheses, but they're pointed. You can also think about them as arrows going in opposite directions. Anytime you see those around a set of numbers or around a variable, that indicates a vector. Okay? Typically, when we talk about vectors and naming them with just a singular variable, we talk about U, V, or A, sometimes B as well. Those are the 4 most common just variable names for a vector.
I thought this was like a ray.
Kind of the same concept, but rays, our 2-dimensional vectors, could be 3, which is why we're thinking about it a little bit differently. Okay, so I mentioned that a vector is a line segment that has a direction and it has magnitude, so we need to talk about what a magnitude of vector is. So the magnitude of a vector is the length of the segment. Or as Colin pointed out, the ray, if that's the way that you look at it. When we talk about magnitude, it is always denoted by a double wall on either side of my vector name or the vector coordinates. So this would be the magnitude of vector V. So if I know the magnitude is simply the length of my vector, that means it's also just the distance between the terminal point and the initial point. So it's just the distance between 2 points, so it should be no surprise that the formula for finding the magnitude of a vector is simply the distance formula. Majority of the time when we are finding the magnitude of something, it will start at the origin, which means that we don't need a secondary point, but I'm going to put a secondary point in there anyway because I like to make things challenging.
How sweet.
Right? Super sweet. Okay, so if I'm looking at the, we'll say we have 2 vectors. Vector 1 is vector A, and it has the coordinates A1 and A2. And then we have vector B, which has the coordinates B1 and B2. The formula for finding the magnitude of that particular vector is going to be the square root of B1 minus A1 squared plus B2 minus A2 squared. It is literally just our distance formula that you learned back in geometry. Hopefully you learned in geometry or algebra. As I mentioned, majority of the time, we will have our initial point starting at the origin, which means it's just x squared plus y squared and then the square root of their sum. But we will do some examples where that'll be more clear. Vectors that have the same magnitude and the same direction are considered to be equivalent, but that's kind of common sense, at least in my opinion. So we don't necessarily need to write that. I'm never going to ask you a question asking like these two are equivalent. Just know that it is possible. Another important thing that we need to know is that a vector that represents a pull or a push is considered a force vector. This is where the physics part comes in. We're not going to do a ton of the physics aspect, but you should see the validity in the application of it.
I wish I could probably a correct answer.
An asterisk is an asterisk. It doesn't need to be perfect.
No, but like the points don't line up in the middle, so it like looks wrong. Oh, you yanked your computer.
Okay, so I'm going to give an example of what a force vector could look like, just so you can kind of visualize it if we ever talk about it again. So let's say that, oh, I don't know, some person is standing here. I do stick figures. I'm so sorry if it's not up to your artistic, I don't know.
Standards.
There you go. I'm sorry, it's what I do. So we have a person here. Let's say it's a pizza delivery guy, because who doesn't love pizza? That's very specific. And this pizza delivery guy is standing here holding a pizza, waiting for you to pay him. What pizza is it? Whatever kind you like. Okay, I have this pizza delivery guy. While this pizza delivery guy is standing there, he's simply holding the pizza. It's not moving. It's just sitting there. Is there any force acting upon that pizza?
Yes.
Yes, gravity. So we can assume that there's gravity acting downward,
He's also
which means that there's also force being applied upward to hold that pizza steady with the gravity acting upon it. This is the most common time that we see force vectors happening, and we just have a capital F to indicate that it's a force. Because there is force being applied to that pizza pushing up against the gravity that is currently pushing down. That's what we mean by a push or a pull. So something moving with other things acting on it. Okay? Again, I'm not really going to ask you a lot about force because this is math and not science, but it's good to know and it's good to see the application. So then what if I have two different vectors and I wanted to know what would happen if I were to put the two vectors together? I know none of you probably wonder that, but we're going to pretend that you do. So let's say, for example, I start with vector AB, and then I want to add to it vector BC. So vector AB started at A and went to B. Vector BC went from B or started at B and went to C. But I want to know what the sum of those two vectors would be. Anybody have an idea just looking at it? Very, very close. Their sum would simply be the vector that connects the initial point and the last terminal point. So my vector AC would be the sum of vector AB and vector BC. Formally written out, vector AC would be vector AB added to vector BC. This is actually called the triangle law because it makes a cool triangle when you draw it out.
no way.
Yeah, it's pretty cool. This only works if my two vectors are connected at a terminal point that then turns into a initial point. There is another law that we're going to look at that happens when my two vectors start at the same initial point and then go in opposite directions. So what that would look like, we'll say they all start at vector A. I have one vector that goes left to point B. I have another vector that goes right to point C. What would the sum of these two vectors be? Huh? Oh, no, it's not another triangle law, actually. It's actually going to be basically the halfway point of where they meet when I add them together. So their sum would be vector AD, wherever AD existed, because that's clearly not drawn correctly. This works because when I connect all of these points, if it were drawn perfectly, it creates a sort of parallelogram. So this is actually called the parallelogram law. This only applies when my two vectors start at the same initial point and head in opposite directions. And it simply says the vector AD would be the sum of my two vectors that split and went in opposite directions. So there are two laws that kind of give us the foundation of how to find the addition of two vectors on a plane depending on how they're situated. Again, mine is not drawn to scale, but that is in theory how it works. So what we're going to do now is we're actually going to start looking at vectors that have numerical components to them. So the component is simply the coordinates that make up the endpoint of each of my vectors. And for this, we're going to assume that we're using vectors that start at the point 0, 0 and end at some point on my coordinate plane. Okay. So this will be our first set of examples. In this set of examples, we are going to sketch each vector. This is where your graphing comes in. And find its magnitude. You guys ready? The first vector that we are going to look at is the vector A equals -3, 2. So my vector is vector A, and it has the coordinates -3, 2. This means that my vector starts at the point 0, 0 and ends at the point -3, 2. So when I sketch this vector, I'm literally drawing my coordinate plane. I'm going to put as many lines on here as I need in order to graph the point correctly. I'm going to put the point -3, 2 on my graph. So I go left 3 and up 2. And then I just draw a line connecting that point I just put down to the origin 0, 0. And you put an arrow on it indicating it has a direction, which makes it a vector. And that is vector A. That is how you sketch this. Does that seem overly difficult to anybody?
No.
No. Okay, we are just plotting the point where my vector ends, and unless it states otherwise, which none of your homework will, we assume that it starts at the point 0, 0, because that's where majority of vectors start. So we did the sketching. What was the other part of the instructions? Find the magnitude. So I would like to find the magnitude of vector A. In order to do this, I have to know the starting point, and I have to know the ending point. So I know it started at the point 0, 0 and ended at the point -3, 2. And I'm going to use this to write out the distance formula and solve it. So my magnitude is equal to the square root of -3 minus 0 squared, because I do x minus x, plus 2 minus 0 squared, because I do y minus y. And then I will simplify it out as far as I can go. I do not want a decimal here. Okay, I do not want one. So if it comes out and I cannot reduce it out of the radical, we leave it under the radical because that is an exact value. So let's simplify this out. What's -3 minus 0?
3. Or -3.
-3. So that is the same as -3 squared. Plus, what's 2 minus 0?
2.
2. So that is 2 squared. And then I just squared that. What's -3 squared? And then what is 2 squared?
4.
What's 9 plus 4? Can I reduce the square root of 13?
No.
So I leave that as my magnitude. If you wanted to write it out, we would just say that the magnitude of A equals the square root of 13. So that magnitude, remember, is simply the length of my vector. Any questions? If I know that my vector starts at the point 0, 0, do I need to write it out like this? Or could I skip straight to this?
Right.
If you see it, you can definitely skip straight to this. Just know that at some point I could throw a vector that doesn't start at 0, 0 on there, and you would have to do the distance formula correctly. So it never hurts to have the distance formula written down somewhere, but if you recognize it starts at 0, 0, then my magnitude is the square root of x squared plus y squared. Okay? Any questions on that one? Let's do another one. So this is going to be vector B. And it has a terminal point or an endpoint of 0, -2. On your own, please sketch this vector. Hopefully we all drew a vector that went straight down 2 units. Did anybody draw it going left? No? At least we're not admitting to it. Okay, remember, when we graph this, because I still see mistakes happen in every class, x goes first, and then we move our y's, okay? So when we did this, we went ahead and graphed it, and we got this vector right here. It's kind of hard to see because it overlaps with my y-axis. That's entirely fine. There's nothing that says that my vector cannot lie on one of my axes. Just make sure that if you're sketching it, you make it extra dark so I can tell this where your vector is, okay? I sketched it. What's the second part of this? Finding my magnitude. Do we need to use the distance formula all expanded and written out with the zeros in it? No, but you're welcome to if you want to. Okay, I'm never going to say no to that because you're guaranteed to get it right as long as all of your math is correct. I'm going to go ahead and do the abbreviated version without the zeros in it, just because we already know it starts at 0, 0. So anything minus 0 just sits up. So my magnitude of B is going to equal the square root of my x coordinate 0 squared plus my y coordinate -2 squared. When I simplify this out, 0 squared is 0, -2 squared is 4, 0 plus 4 is 4. Does that reduce?
Yeah.
Into what?
2.
Okay. It technically reduces into 2 and -2. I did hear somebody say it. However, do we ever use a negative length? No. So we automatically assume when we're taking the square root, we're only taking the positive square root. So my magnitude of vector B is 2. Of course, we could have just counted that on the graph and gotten the same answer, but it's a lot harder when we have something moving at a diagonal. Questions, concerns, or issues thus far? Anybody kind of like vectors so far? We haven't done a whole lot with them, so it's still very introductory.
We know this is like the baby step, so it's not, we're not going to say yes yet.
But we should only hit baby steps today. I'm saving the fun stuff for tomorrow.
So what's Wednesday?
You just wait. Okay, so this one is yours to do entirely on your own. You are going to love it.
Sounds really good.
I bet you are.
It was a very big tray. Bro, stop.
Of course, you asked that question right before you did.
I know. It's very strategic of me.
Give them, take it away.
It's just they're just here.
Again, I'm asking you to sketch this vector and find its magnitude. Don't get freaked out by the fractions, just numbers.
They're just numbers, man.
I've missed all of you, just so you know that. So glad we're back.
Oh, I'm dumb.
You said it, buddy.
Thank you for the reassurance, Gabe. I should have done this a little different. Oh. Thank you. I still have numbers. So where do the lockers go? They're in the mezzanine.
Yeah, they just moved them out because they're going to redo the hallway walls. And you can't do that with the lockers. At least, that's a weird.
Oh, it's like,
It is
I thought it was
so
sliding.
Huh?
Oh.
They have them in the same hallway.
Oh, they moved it once down.
Oh, as far as I knew, they purposefully gave people lockers in the
I
same
know they
hallway.
did that.
Oh.
But there were some upstairs, though.
Hope they move their stuff first.
I would
How did they
imagine.
do? Oh, I hope so too. I'm sure they did.
I hope they didn't. 'Cause that
Okay,
means
who wants to come up and sketch this vector?
I could sketch it, but I'm not doing any more
Okay,
of
let's go, Colin.
that. I did it wrong at first. Too, so.
I'm proud of you.
Oh my gosh.
You're welcome. No, like here.
No, just use the side of your hand. That was the worst C I've ever seen in my life.
My handwriting.
Okay, show of hands. Who else got a vector approximately in that area? Hopefully all of you. It doesn't have to be perfect because these were clearly decimals, so this would be 0.8 and 0.6. So we expected it to be closer to the one here than the one there. Obviously, you're freehanding these, so I don't need them to be exact. But you definitely shouldn't have gone beyond one on any of those axes. Anybody have an issue with sketching that?
You just draw the numbers and make it better. Like, they just put 4 fifths on the bottom.
Yeah. Okay. Yeah. Okay, so then what was the other portion of this? Magnitude. Who would like to do that for us?
Can't believe you just erased
I know. Trent, you're up.
patterns.
The pen is here. Show of hands, who else got 1 as the magnitude of this vector? That is 100% correct.
You did.
Okay, so
Oh, 16. Oh my God.
yeah, so when we square a fraction, because I see this happen a lot as well, you square the top and the bottom individually. Then he went ahead and put these two fractions together because they both have the same denominator, which gave me 25 over 25, which reduces to 1, and then we take the positive square root of that. There is actually a special name for a vector that has a magnitude of 1, and it is called the unit vector. This will be helpful tomorrow.
Outside of that,
The unit vector is very helpful in some things that we're going to be doing tomorrow and a little bit later on. And it has quite a few applications in the mathematical and science worlds. This is terrible. So I wanted to go ahead and introduce it here. Any major questions, concerns, or issues with sketching these vectors and finding their magnitudes?
Square root is 20, right?
Absolutely. Okay, so what we're going to do now is we're going to kind of back off of the whole magnitude thing, and we're going to start combining vectors. So we're going to combine them through addition, subtraction, and scalar multiplication. Okay, so we're going to start with addition and subtraction first, and then I will introduce the scalar multiplication, and then we're just going to kind of stop there today. Okay?
Yay.
I know you're so excited. So let's say I have two vectors, A and B, again, with their components also being the same variable. So vector A has components A1 and A2. Those simply mean the coordinates that make up the endpoint of that vector. Vector B then has components B1 and B2, and we're going to add them together. So I want to find A plus B. The first thing I'm going to do is I'm going to write out the vectors that I'm putting together so that you can see how we can put their coordinates together. So vector A is again A1, A2, and then vector B is B1, B2. So when we add or subtract vectors together, we add like coordinates. So that means I'm going to be putting my x's together to create my new x, and I'm going to be putting my y's together to create my new y. So when I add these together, I'm going to put A1 and B1 together. And then whatever they add up to B will become the new x coordinate or first component for my new vector. My second component then is going to be A2 and B2 added together. It's addition because that was the operation that I was given in the original problem. And then whatever those simplified out to be would be the new components for my new addition vector. It's that simple. The same thing would work then if I were doing subtraction. So what if I wanted to do A minus B using these same two initial vectors? Same concept, I would write out what my vectors are, put subtraction between them because that's the operation that I am having you perform. And then we subtract like components or like coordinates, if that's how you want to think about it. Make sure we are always moving from left to right. So for addition, it doesn't really matter. For subtraction, it does. Yes?
So when we do the addition or subtraction or whatever, can we then find the magnitude and that's the answer? Or?
No, technically, I didn't ask you to find the magnitude, so I just found the new addition vector. So A plus B would be whatever this new vector is. That's what we found. So A minus B then would become A1 minus B1 as my first component, and then A2 minus B2 for my second component. As Gabe pointed out, we're not finding anything other than a new vector. So my new vector would be vector A minus B and it would be equal to whatever those reduced components come out to be.
If I used capital letters, would that be okay?
That's fine as long as you stay consistent.
Okay.
Okay? Anybody super confused by that? Of course, we're going to do some actual numerical examples, but I wanted to go ahead and throw these in here first. Okay, so let's do some examples. Let's go ahead and say that our first vector A is vector 3, -4, and my second vector B is the vector 2, 7. I would like to find both A plus B and B minus A. I would also like to point out that from here forward, I'm going to be crossing my 7s, because if I start like writing a lot, these end arrows start turning into 7s. So make sure you're aware of that in your own handwriting, because if you don't, that could turn into a 77 really easily, and then that'll throw off all of the rest of your numbers. Okay? The first one I want to do is A plus B. So that's going to be the first vector I find. Again, I like to write out what my original vectors are. Makes it a lot easier for me. So my first vector A is 3, -4, and I'm adding to it the vector 2, 7. I'm going to put like components together. So 3 plus 2 is going to be my first component. And it's addition because that's the operation I was performing. And then I'm going to have -4 plus 7 as my second component, and then I'm just going to simplify that. You don't have to write this step if you see what's happening, okay? So when I simplify, 3 plus 2 is 5, and then -4 plus 7 is 3. So my new vector, A plus B, is the vector 5, 3. Questions, concerns, or issues so far? Does that make sense how we did that? Is anybody super duper confused? On your own, find vector B minus A then, please.
Oh, it's B minus.
Yes, it is B minus A. Make sure you're paying attention to the order. Anybody else getting the same vector that I got? So -111. Anybody not getting it to work out to that? We're just a little short on time, so I tried to go ahead and get the work down so we can look at it.
Thank you.
Anybody running into issues? No. So we're feeling pretty much okay with all of this, right?
Fair.
1 to 5, how are we feeling so far? Lots of 4s and 5s. That makes me so happy. It's easier than you think it's going to be. Okay, so we're going to do one last little thing today, and then we're going to stop. I do want to point out that there's a very big difference between multiplying vectors together and doing scalar multiplication. Today we are just doing the scalar. I'm also going to tell you that you're no longer using a dot to indicate multiplication here. I don't care if you use an asterisk. I don't care if you use a little X. You cannot use a dot because it means something else that we're going to cover later. Okay? So for multiplication, you're no longer using a dot.
Okay. Okay.
Okay.
First you get rid of the X and then you get rid of the dot.
I know, I'm sorry. So this is scalar multiplication. It sounds a lot scarier than it is. Because scalar just means singular value. So scalar multiplication is literally taking one number and multiplying it into a vector. So formally written out without numbers, this would be a scalar m. M and n are often the variables we use for scalar. You can pretty much use anything, but that's what we're going to use here. So this is scalar m being multiplied into vector A. So A1, A2 is my components. When we multiply a single value into a vector, it distributes just like it has previously in algebra. So that singular scalar value multiplies into both of the components individually, creating a new vector. So this becomes the vector m times A1, m times A2. And then, of course, we would simplify it to get the new components. That is all scalar multiplication in vectors is. Again, you are not using a dot here for multiplication. Please remember that. You can when we're done with vectors, but not till we're finished.
I'm just going to use an X for now.
So let's do some numerical examples, and then I'm going to call it a day. And by some, I mean two. So the first one I would like to do is given vector A equal to -3, 4, and vector B equal to, I'll say -2, -3. I would like to find 5A to start with. So I'm showing it to you this way because this is the way that your homework will show it to you, and I don't want you to be confused. This simply means we're taking the scalar 5 and multiplying it into vector A. So this is the same as 5 times my vector, -3, 4. And then I would just multiply that 5 into both of the components, and then we'll simplify from there. So then this becomes 5 times -3 and 5 times 4, which then simplifies into -15, 20. So my new scalar vector, 5A, is equal to the coordinates -15, 20. Questions, concerns, or issues thus far? Does that make sense to us all? Okay. I'm not going to make you do another one for B, but I do want to show you that these things can be put together because they will on your homework. We don't have to solve it necessarily, but I want to talk through how you would potentially solve a problem like this one I'm about to show you. So on your homework, it's going to give you ones like this. So using vector A and vector B from above, we're going to go ahead and set this one up. We won't have to solve it because once you see how it's set up, you'll be able to solve it on your own. But I don't want you to get confused by what it's asking. This simply means that I need to perform a scalar multiplication on these individual vectors first, and then I'm going to subtract them. So then this would be the same as 4 times my vector A minus 3 times my vector B. Just like we do in order of operations, we perform the multiplication first, and then we do the addition or the subtraction. So I would multiply this 4 into both of these components in the first vector, and multiply the 3 into both of these components in the second vector, and then subtract from left to right. So then this would become negative 12, 16 minus negative 6, negative 9. It's very important when we have subtraction and scalar multiplication happening that we multiply just the positive version of this into that second vector. That way we can still subtract. If you wanted to multiply the negative in, that's okay, but then this would turn to addition, so I don't recommend it because you often forget this. And by you, I just mean students in general. And then we would subtract from left to right. So I would do the negative 12 minus the negative 6 and the 16 minus the negative 9 to get my new 4a minus 3b vector. I guess might as well finish it. We're already here. And you should get negative 6 and 25. Does that make sense? Honestly, in my opinion, this is the hardest that what you're doing today is going to get for your homework. Okay. So your homework is 10 questions. You should be at least able to do, I think, 5 of them right now. And then we will finish up this lesson tomorrow. Sound good? Awesome. Thank you so much.
What am I doing wrong?